So, let us start this lecture with a thought process from Marcel Proust. The real voyage of discovery consists not seeking new landscape, but in seeing through new eyes. So, we will do as usual, like we will recall what we learnt in the last lecture. We basically looked at how one can derive the first law of thermodynamics for an open system, and then we have also looked at the steady state problems and how one can apply this first law of thermodynamics, and we took also an example in the last lecture for turbine, and where we had seen that if you neglect the kinetic energy and potential energy terms, I mean you will not really commit much error in that, because very negligibly small. And what we will do today, we will be looking at basically unsteady flow process, right, because in the last lecture we have dealt with the steady flow process. Of course, it occurs, but there are several unsteady flow processes which are very common in in engineering applications and also day to day life. So, how we will apply that? That is the question will be. So, what are the examples you are aware about unsteady flow process? Can anybody tell me? Which will be unsteady, that means you can't afford to apply, say that look, the process is steady. You must be knowing, I am like, am I right? For example, like you might have seen that you want to inflate a balloon, or you want to inflate your tire, or sorry, tube, you want to inflate your tube with the air, right, high pressure. So, that is a steady process or unsteady process? That will be cannot be considered as a steady process, because it will be go on changing, right. And there are any other examples comes to your mind? So, if you look at like your pressure cooker, let us say, right. In the pressure cooker, when you heat, I mean you boil some vegetables and other things, what will happen? It will be pressure will be goes on building up, and then some mass will be going out and till it reaches certain pressure, right. So, there are several examples one can think of, as I told, domestic pressure cooker, inflation of a balloon, charging of tank, and we can think of like driving a gas turbine from a pressurized tank, right, or any other kind of, you can also drive a piston engine or some other kind of system. For example, we are having power cut. Now, you can think of using some kind of stored energy and then use that, like I can charge some high temperature gas or the a high temperature and pressure gas in a tank, and then allow it to flow through some device, and which can give me generate some electricity, one can think of. And of course, the running of rocket motors by the pressurized air, and several other of them one can think of. So, if you look at this is a typical pressure cooker, what I have shown here, right, and some it being heated with some heat, right. And then if you look at, this is your pressure regulating valve, right, which you might have seen in your home. What happens whenever this pressure is built up, because heat is there, let us say this is some kind of water you are boiling with a vegetable, then it will be vaporizing. So, these are basically vapors, right. And then the pressure will build up, and when it will be reach the more than the weight, which will be like you put a weight basically, and that weight, if the pressure the applied by the vapor is will be applying a force, and that will be higher than the weight, then that what we call it is basically petcock, or the pressure regulator is a weight one, and then it will go up, and then some amount of steam which will be released, and again it will come back, and again it will build up. So, this is basically unsteady process. Now, this kind of things we can apply in several other places. So, you might be aware, like like we are having, let us say, a biogas plant. You have seen, any of you have seen biogas plant? What we call gobar gas, plant in village, rural areas. Suppose I want to generate some gas, what I will have to do? And it should be at high pressure, right? How I will make pressure? Then what we will do? There will be dome, on that I will put some weight, and the gas will be collected, pressure will increase, I can use that one, right. So, there might be several application one can think of, and let us say we want to charging a a cylinder, and like there might be charging of your nitrogen gas cylinder, hydrogen gas cylinder, even in your LPG gas cylinder, what you get, LPG you will be knowing, like liquid petroleum gas, right. Is it a gas, or is it in the cylinder, what it will be containing in LPG cylinder? It is basically liquid, but when it will be released to atmospheric pressure, then it will be a gas, converted into gas, right. So, right, that suppose you want to, it will be collecting from somewhere. So, you will have to charge those cylinders, and for that, let us say there is a supply gas, and you are having a valve over here, and if it is there, then it will be coming over to this cylinder. This is basically a gas cylinder, and in the beginning, of course, it will be evacuated, right. You should not have anything in principle, or you will have to, or it will be at a very low pressure, so that this pressure will be higher, gas will become and fill it up, and then it will be till it attains some equilibrium pressure, then you will remove, and there will be some mass is changing in this gas all the time, right. And so also the pressure, temperature in this cylinder will be changing. Now, you need to analyze these problems, right. So, and there will be several other problems, unsteady problems, phenomena which we need to analyze, and how we will do that we are going to see. And there is another this thing, what it will be coming is basically the piston cylinder arrangement. So, in that, suppose there is a piston here, and you are putting some gas kind of things, right. And in this case, what is happening, if you take this control volume here, right, and this control volume is changing its position as the gas being filled and the pressure being higher, right. So, that piston will be moving, right. So, this is also another unsteady phenomena which will be occurring most of your automobile engines, right, is not it? Gas will be, or air will be entering, and then it will be going out. So, that how we are going to model is one question which we need to address. So, see, unsteady process means basically process which changes with time, we call it also transient process, and this unsteady process will be starting and ending within certain finite time, right. It may be few seconds, it may be few hours, or it may be few minutes, that way it will be. And as I told, the charging of a cylinder, I am like one has to look at it, is one of the examples. And in this case, what is happening, the mass of the gas, like which will be entering into this, and the gas mass will be changing. So, also the pressure, if I say pressure and temperature, it will be changing, like, okay. If you look at pressure will increase, is it the temperature will increase or not, that one has to see, okay. So, basically the properties and the mass of the gas inside this cylinder will be changing continuously, with time. So, therefore, we call it as an unsteady process. So, what we will do, we will have to now apply basically mass conservation equation, and in this case, in this example of basically charging up a cylinder, if you consider, I can take this as a basically control surface and this is my control volume, right. The mass will be entering here and it is not going out. So, if you look at, this is my inlet, right, and there is no exit. So, if I love to look at the mass conservation and this, there is no exit, right. So, therefore, this will be 0, right, this will be 0. So, now we similarly we will apply the energy conservation equation, right, which is for unsteady state. And if you look at this term in the steady state, we had neglected, this is your unsteady term. Right, this we had neglected in case of steady state, we are saying it is 0, but here we cannot afford to say it is to be 0 or neglected, right. Here we will have to consider that. And of course, if we consider in this case, is there any work done in this case? There is no work done, it is a charging. So, this will be 0. And we can assume to be adiabatic, or we need not to assume the process to be adiabatic. So, right, and what we will do, we will assume that change in potential energy, this is equal to 0. For example, this height is not really much having any effect, right. So, this potential energy, this will be 0 change, and we are saying that like the velocity with which it is entering into this chamber is very, very small. Of course, it will be finite, it cannot be 0, it will be finite, but this is small. So, therefore, the change in kinetic energy is 0 basically, right. And then we can write down the first law of the thermodynamics for an open system becomes, right, dE by dt minus m dot hi is equal to q dot. And here we are saying that it need not to be adiabatic, but in some problem we may assume to be adiabatic depending on the problem. Here we have kept that term with us. Now, if you look at, we need to integrate this equation basically to find out, right. And then if I integrate this over here dt and similarly dt here, so we can integrate between time 0 to t and we will see how we can change. And keep in mind that m is the mass of the gas in the control volume at any instant of time. And of course, U is the specific internal energy of the gas in the control volume at any instant of time, that already we have defined. So, by integrating this equation 1, we can get this, right. Now, we will have to see how we are going to like integrate this, that is the important point one has to see. Keep in mind that in this term, like here, I have taken the h, this term I have taken the hi out. That means, we are saying that whatever enthalpy with which it is entering into this control volume is not changing with time. Okay. Is it a good assumption or a bad assumption? Because we are having it's a, you can say this supply is having a constant enthalpy, kind of things, and which is not changing, and this is, you can say that heat loss is not really much. So, and there is not much change. So, therefore, I can take Hi out, and we will look at each term of this, each term of these terms, and then see how we can integrate. And before that, we will do that, like something uniform flow processes, because if you look at like flow need not to be uniform, but here we will be considering in this case that we are assuming the uniform flow process, and the state in the control volume remains uniform throughout any instant of time, right. For example, like if you look at, if the some mass is entering here with certain thing, and then it will having, and there is a heat transfer taking place, because not adiabatic, some heat will be going out, all the side. So, what will happen? The temperature may change, right. But however, we are assuming that throughout this control volume, right, this is control surface, this is my control volume, that is not changing. That is the assumption we have. Therefore, we are calling it uniform, but in actual situation it won't be. So, of course, so as with time, it becomes 60 degrees Celsius. Now, question arises, will it increase or will it decrease, right? But I have just given, so you think about it, you may solve some problem and look at it, and whether it will be increasing or decreasing. I have just taken some example here. So, at the inlet, flow is assumed to be steady and uniform, right. That is the point. For example, in a flow, if it is coming over here, let us say the flow profile, it can be like this, right. Yes or no? Because of boundary layer will be there, it is a pipe. See here, there will be boundary layer, means kind of things. So, this is a wall surface, wall of the pipe. But however, what we will be assuming? We will be assuming as a uniform velocity profile. That means the profile will be uniform, is all same velocity. And if it is a, let us say, parabolic profile, this is the parabolic profile, then we will say average velocity, and then we can say work it out, and we are assuming that uniform velocity at the inlet and uniform in the throughout. Keep in mind that in thermodynamics, most of the time we will be looking at uniform velocity profile and temperature profile, other thing at the inlet and exit, unlike in fluid mechanics, where you will have to, you can't afford to consider uniform. Okay. So, anyway, in thermodynamics we will be doing, but unless otherwise it is given. So, if it is given non-uniform, then you will have to handle how, in a little different way. So, the state of the gas in supply line remain constant. There is a supply line here which is not shown, this is your supply line, right, and this remains constant, that we are assuming. And let us look at each term, and if I consider this term like this, if you consider this term and then write down here, we will get basically the what you call between 0 to in initial state to the final state, that will be mf uf minus m naught u naught, right. That is the thing by integration we will get. And where the m naught is the initial mass in the control volume at time t is equal to 0, mf is the final mass in the control volume at time t plus dt, and similarly the internal energy uf and u naught, right. So, if you look at this term, right, q dot, this term I can take this out, and this is q dot dt in 0 to final became q. We are saying total heat transfer from the control volume during time dt. So, and we will have to look at the last term, from the mass conservation we know dm by dt is equal to m dot I, and if you can integrate this thing, I mean this is basically you can say 0 to f, right. I mean you can say t or you can say f final, f here, and then you will find out this mf minus m naught, that is right. So, this portion will be like that. So, what we will do, we will substitute these values in equation 2, all these things, and we will get that this h m I dt nothing but mf minus m naught h I is equal to change in your internal energy terms, right, this term. So, this term is basically mf uf minus m naught u naught, and then q dot dt basically q. So, what he says is basically that change in what you call the amount of mass whatever is changing in the cylinder into the enthalpy is equal to the change in internal energy, right, final and initial, right, and minus q naught. If for the adiabatic process, you can make it 0 for adiabatic process, right. The q will be 0. So, this term will be 0 basically, and you will find out is nothing but your enthalpy change in the what you call in the cylinder is equal to change in internal energy, kind of things one can think of. So, now let us look at the discharging of gas from a cylinder, right. Earlier we have seen the charging of a cylinder, now we will be looking at discharging of a cylinder. And in this case, we will consider that a gas which is there at certain pressure, let us say initial pressure of P naught and let us say T naught, right, and it is going out by this valve, right, and this is your control volume, and this is your control surface, and this is your control volume I have taken, and it is going out with certain velocity, of course, will be right, and this is your you can say exit, right. It will be you can say with certain velocity it will be going VE, and as the gas is going out, you will see that pressure and temperature of this gas in this cylinder will be decreasing with time, right, yes or no. And so also the mass whatever containing in this cylinder will be decreasing, and therefore, it is an unsteady process. Now, we need to apply, we will take a control volume as I told, and we will apply the first law of thermodynamics in this case, and of course, we have already know that there is no work being done during this process or on the system or by the system. So, therefore, the work done will be definitely 0, and the change in potential energy will be 0 in this case, right, and there is no inlet. So, therefore, this portion will be 0, and here of course, if you look at the MI mass also this will be 0, I mean this is 0. So, this term will not be there. So, however, we are saying that it will be having certain amount of velocity with which it will be going, right. So, then the energy equation becomes d by dt plus m dot E into He, that is enthalpy which it is exiting, and with the V square divided by 2 is equal to Q dot. So, we will have to integrate this equation, right, and before that we will have to look at mass conservation, that is dm by dt is equal to minus m dot E, because m dot I is basically 0, right, m dot I is 0. So, therefore, it became dm dt is equal to minus m dot E. And if we integrate this equation 0 to t time, that you will get mf minus m naught, right. So, now we will try to integrate the energy equation, right, and integrating this will basically between the time 0 to certain time t, and we look at each term. Already we have done, it will be similar to that, like d by dt is nothing but your mf and uf minus m naught u naught, and in the similar way we can also integrate m dot E h e plus v square divided by 2 this into dt, and we are assuming that this is not changing, right, this is constant, not changing, this term, right, h e plus v square by 2 is not changing with respect to time, right. Therefore, I will take it out and then we will get m naught minus m f into h e plus v square divided by 2, right. Keep in mind that here I have taken a minus sign because the mass is going out, and then rather, in other words, the mass of the cylinder is decreasing, right. Therefore, the negative sign is taken, so it became positive kind of thing here. So, this is assumption, if you look at, is not really right unless otherwise you are taking out very small amount of mass from the cylinder, which is at a very high pressure and high temperature or high pressure, rather amount of mass in the cylinder is very high, and you are taking very small amount, so that velocity will not be changing because pressure is not falling so drastically, right. Then only, otherwise velocity will be changing because it is going to, let us say, ambient pressure, let us say, for example, right. Then the pressure of the cylinder is changing, and at ambient will be remaining same. So, therefore, the pressure gradient changing, velocity has to change, but we are assuming it is not changing with respect to time for simplification, right. So, that you should keep in mind. So, and equation 5 becomes, right, m naught minus m f, sorry, equation 3 becomes m naught minus f f into h e plus v square divided by 2 is equal to q plus m naught u naught minus m naught m f u f, right. So, this is the things equation what you will get for the discharging of a cylinder, right. So, it is similar to that, right, except that we are considering little kinetic energy or the exit velocity here, that is all, right, not really much, and right. So, this way you can handle these problems. Let me tell you, like suppose here we have assumed a control volume approach for charging and discharging of cylinder unsteady process. Suppose I want to use the control mass system or a closed system, and I want to analyze this problem. Is it possible or not? Can I arrive at same equation or not? It is possible, you can do that, and I would suggest you do it yourself and have a feel, because it is important to appreciate that any approach you can do, like either control volume or control mass system for any thermodynamic problem. But however, one has to be little careful, and sometimes one will be convenient for certain kind of, for example, for problems, control volume approach is convenient. That does not mean you cannot apply the control mass system there, right. So, that you should keep in mind. And let us see that another application of these open flow problems, that is the heat exchanger. like heat exchanger is being used routinely in industries to have a heat exchange, between two fluids or maybe, and without really getting mixed. That is the thing, but there might be another place where the fluid will be mixed together, right? It is like a mixture. What we do in your shower, like whenever you take bath in the winter season, that hot water and cold water with the help of a tea or something you will be mixing and then getting a water which is moderate enough for your body or this thing. Otherwise, if you take a directly the water from your geyser, then it will be having problem, right? Isn't it? Unless otherwise it is controlled properly. So, heat exchangers are widely used in various industries, and there are also various kinds depending upon the application and also depending upon the designer what they can think of. So, if you look at application wise, there are several, like your cooler, like what we use the desert cooler, like can you think of desert cooler is a heat exchanger? Can you call? In this definition, it is not really, right? It will be rather comes under a mixture. And like heater, radiators in the car, that is a very good heat exchanger. And in the recuperative kind of combustors, we do exchange the heat, and so that you can preheat your air and other things. Of course, power plant, refrigerator system, several. I mean, heat exchanger is a very, important component what people use in industries and other places. So, heat exchangers can be several type: concentric tube type, cell tube type, cross flow type, compact heat exchanger. I mean, several of them one can think of. Those people who are in mechanical engineering, they will be learning this about heat exchangers in detail. So, let us consider that a heat exchanger, a cell and a tube type kind of heat exchanger, like you can say that concentric tube type heat exchanger, in which case the fluid A is coming with 20 degree Celsius and leaving with 50 degree Celsius, because the fluid B which is entering into this, which will be come in contact with the cold fluid which is at 70 degree Celsius, and it is leaving at 35 degree Celsius, because there is a heat exchange which is taking place without really getting mixed, right. This not, and there will be. Now, if you want to analyze this problem, right, so you will have to like take care of how to take a control volume of that. See, this is a simply simpler kind of system. So, let us look at the another kind of heat exchanger, in which if you look at your cold or the water is coming over here and it is going kind of things through the tube, right. It is going through these tubes, right. Again it is coming to another chamber and it is again going back, and then the steam which is at high temperature, it will be coming, these are the baffles, so that it will give more resistance, again pass through this way, like if you look at it will be passing through this way and this way, again these three, so that more contact, more residence time will be given and the heat exchange will be, and this is basically kind of a complex heat exchanger kind of things. And you want to analyze this kind of problem, you will have to simplify the things, and we will see now look at a concentric tube heat exchanger. And one can think of using two control volume, like if I put it this way, that in this case this is your control volume boundary, like these are the control volume, and which include both the cold fluid pipe and also the hot fluid pipe. And in this case, if I take this as a system, we will consider the heat exchange in this control volume is 0. But if I take the other example, like the same example, but I will choose this control volume here, right, this is my control volume. So, then like you will have to consider how much heat is passing through this surface, there will be some kind of heat which is passing through this control volume, right, and this here you will have to take care. So, what I am trying to emphasize here, that whenever you choose a control volume for a particular analysis, you will have to be very careful to handle the things, right. Otherwise, you will be in trouble. So, let us consider this thing, how we are going to that, like fluid 1 is passing through this, and which is having what you call m dot IV, the inlet, right, and this is with the enthalpy at the for the one enthalpy at the inlet for this fluid 1, and similarly it is the fluid 2, it is entering with a certain mass flow rate and the enthalpy, and it is being cooled down, and then this heat being transferred to the cold fluid, and then become the fluid temperature increases. So, if you look at, we are taking this as a control volume, as a result there is no heat being transferred, like Q dot is basically 0, equal to 0, because all the heat is the exchange of the fluid from the fluid 2 to the fluid 1. So, mass conservation equation we can get, because this is a steady flow process. So, dm dt is equal to 0. So, therefore, you will get basically mass flow rate at the inlet for the fluid 1 is equal to mass flow rate at the exit for the fluid 1 is equal to m dot 1. Similarly, for the fluid 2, that is m dot 2 I is equal to m dot 2 E is equal to m dot 2. So, and what we will do now, we will basically apply this first law of thermodynamics for this control volume. And if you look at in this term, what we are doing, we are basically making these assumptions, that is the change in potential energy is 0, right, and there is no work done here. And what about heat? Heat also is, there is no heat exchange, right, between the control volume, because control volume, in that control volume both the fluid are embedded. So, therefore, that will be 0, and change in the kinetic energy also is equal to 0. So, therefore, you can get the first law of thermodynamics as very simple, that is enthalpy balance, and that is the total enthalpy at the what you call for the fluid 1 at the exit plus the total enthalpy for the fluid 2 at the exit is equal to total enthalpy at the inlet for the fluid 1 and for the fluid 2. That is all, is basically enthalpy balance, nothing else. And from the mass conservation equation, we already know this, right, that is this thing. So, that what we will do, we will basically put this equation over here and then simplify, and then we can write down as m dot 1 into He minus Hi at the what you call for fluid 1. That means the whatever the total enthalpy of a fluid is equal to total enthalpy for the fluid 2. That means total enthalpy for the fluid 1 is equal to total enthalpy for the fluid 2. It's a very simple way of looking at it. I mean, you need not to really do this equation to look at it, but if you just keep it and do that balance, then it will be good enough. So, let us look at another process, what we call is a throttling process. In this case, there will be significant drop in fluid pressure. Where these processes will be occurring in our this thing? Any idea? Because there will be significant pressure drop. For example, you have already seen the turbine, right? In the turbine or in the compressor, there will be significant pressure drop, right? Yes or no? Yes or no? See, if you look at fan the pressure will be increasing little bit. The pressure drop means basically pressure will be decreasing in this case, you can say. So, it will be in the case of turbine, there will be significant drop in the pressure, because the right. And but however, we are not discussing about that. Here we are discussing about a valve. Like suppose you are having we have seen that there is a discharge kind of a from a high pressure gas cylinder, and that valve when I open, there is a lot of pressure difference, like in a cylinder of let's say nitrogen gas cylinder or hydrogen gas cylinder, it will be let's say 100 atmospheric pressure or maybe 500 atmospheric pressure, it is there, and then the change it to the 1 atmosphere is a very significant drop change, from let's say 500 atmospheric to the 1 atmospheric pressure. So, that drop with it will be occurring across a valve, because there will be a control valve which will be controlling the thing. So, the throttling valves are any kind of flow restriction, it will be restricting the flow device that causes significant pressure drop in the fluid. And as I told that what is the difference between a turbine and throttling valve? The turbine, if there is a pressure drop, there will be work done, right? That means work, mechanical work being done. But in this case, there is no work done as such, because if you look at, there is a discharging of a cylinder or a gas from a high pressure cylinder is going out, there won't be any work done as such, right? So, there are various kinds of throttling valves which you will be knowing, but let me just tell you few of them. The one is the valve, like when it is open or half open or kind of things, there will be a throttling process, there will be significant change in pressure drop. There is a porous plug, and there will be capillary tube. You might be knowing what is a capillary tube, right? You are aware? It is a very thin tube, thin and a small diameter tube, thin wall, like your hypodermic needle, whatever you use for injection, that can be used as a capillary tube as such. So, if you look at, these are the diagram, what you can keep in mind, this is adjustable valve and there is a porous plug and there is a capillary tube which is very small kind of things, the small diameter tube. And this pressure drop in the fluid is often accompanied by the large drop in temperature, right? And for that reason, the throttling devices are commonly used in refrigeration air conditioning system. Did you observe any time, maybe in your chemistry lab or some other things, you might have opened a high pressure cylinder gas, and then you will find that particularly in the winter season, like you will find some condensation is occurring across that tube. You have observed? Any of you have observed or not? You have not seen? Please see it whenever you do some experiments. Like why it is happening? Because the temperature is coming down very low and the moisture is there in the atmospheric air, it will condense on the top of it, and you can see that. So, therefore, that is why it is being used. Of course, you must not have seen your refrigerators. There will be something, throttling valve will be there, and you see there is a tube, which the capillary tube being used, to reduce the pressure so that you will get the cooling effect. And this experiment basically done by the Joules and also Thomsons. So, what they did, like there is a porous plug one can think of, and taking and then there is a pressure, high pressure P at the inlet Pi and temperature Ti. Of course, it will be having some enthalpy of the fluid, and when it pass through, that pressure Pe will be reduced, and temperature Te it may change, it will be changing, it may be reduced or it may be enhanced, and then enthalpy also will be changing at the exit. So, this assumption, let us say we can say there is no, if I take this control volume, right, for the porous plug here, this is my control volume. So, what will happen? Is there any heat will be going through? So, if you look at these are very small kind of this thing, the heat is very heat transfer will be 0, there will not be any heat transfer as such, and there is no work done. So, therefore, the shaft work will be 0, and we are saying that the change in kinetic energy is 0, because there will not be any much velocity change which will be occurring, and so also the change in potential energy is equal to 0. And we can assume this process to be steady, right, and there is no unsteadiness as such is there we are considering. And then with this assumption one can really use this equation and then make this is basically 0, and this change in potential energy 0, change in kinetic energy is equal to 0. What it amounts to be? Amounts to be that the enthalpy at Hi is equal to He, and we have also from the what to call from the mass conservation equation we can write down that m dot E is equal to m dot I is equal to m dot. So, therefore, either the specific enthalpy or the total enthalpy is remaining constant. We have seen similar thing in your heat exchanger, and this process is known as isenthalpic process, right. Throttling is basically is an isenthalpic process, and so if I just rewrite this enthalpy in terms of the internal energy, you can say that internal energy, this is basically internal energy, and this is what? This is your flow work. So, and that is at the inlet and equal to the again internal energy and the flow work at the exit. So, if you consider that PEVE, that is the flow work, right, this is the flow work, is at the exit is greater than the flow work at the inlet, then UE, that is internal energy at the exit, will be less than UI. And if you assume that CV is not really changing much with this temperature change, then you can happily say that TE is less than TI. Okay. And similarly, if the flow work at the exit is less than the flow work at the inlet, this other way around, that internal energy at the exit greater than the internal energy at the inlet, and T exit temperature will be greater than Ti, right. So, is it really will be occurring this kind of thing? That means that it will be higher than that, right. Suppose you take a nitrogen gas cylinder and you open the valve, from a high pressure the gas will be going, and take a hydrogen cylinder and open a valve and and then there will be throttling process will be taking place. What will happen there? Right? You think about that, we will come to this. So, but for an ideal gas, the enthalpy, we know that TE is equal to TI, that means, right, because the enthalpy is a function of temperature only, right. And for as I told that they have conducted experiment by keeping this what you call Pi, Ti constant and then varying the Pe by the throttling valve, and you can change this thing. So, if you conduct these experiments, like you take this Pi and then goes on changing the Pe, and then you will get different temperature, you will get that it is increasing, then it is remain reaching almost there is no change here, and then again it is decreasing, and this is the inverse point, because the slope is changing from the what you call right hand side to the left hand side. If you conduct this experiment, several of them, and of different inlet conditions, you will get various curves like that, and if I join this inversion point, like where the slope is 0, right, then what will happen? This curve is known as inversion curve, right, and in this region, like we call it a region of cooling, and in this region we call it as a region of heating. So, then we can define a term, the Joule-Thomson coefficient is where mu Jt is dou T by dou P, and H is enthalpy is remaining constant, and this is a property of the system which will be being used, and we will also be discussing this about whenever we will go for how to evaluate this in terms of measurable properties, right, we will discuss that. And so, this if you look at this point is joining, if you look at this is a maximum inversion point, if you join over here, that is the temperature corresponding, and if you consider this mu Jt is equal to basically Te minus Ti divided by Pe minus Pi, when mu Jt is greater than 0, right, that is in this region, what will happen? Pe is less than Pi all the time, because pressure will be lower, Pe is less than, then what happen? Te is less than Ti, therefore, this is cooling region, right, this will be cooling region. And when mu Jt is less than 0, this region, right, when Pe is less than Pi and Te is greater than Ti, heating region, right. So, as I told, like particularly when you handle this hydrogen kind of gas, there you will get this heating up, therefore, one has to be careful when you are handling the hydrogen cylinder kind of things. For almost all gases at ambient temperature, mu Jt is greater than 0, that is cooling, right, and exception in hydrogen, helium, neon, these gases one has to be, and of course, helium and neon is the inert gases, so therefore, no problem, but hydrogen is a very reactive gas, so therefore, one has to, and for hydrogen the inversion temperature 2000 Kelvin kind of thing. So, on throttle at the ambient temperature, T is greater than Ti, if it is higher temperature, then if there is a leakage, then it may ignite the mixtures around that place. So, there will be explosive kind of things. So, therefore, one has to be very careful handle the hydrogen cylinder for avoiding the explosion. So, knowledge of inversion curve for real gases is essential to design refrigeration liquefaction systems kind of things. Therefore, one has to understand these properties of the Joule-Thomson coefficient, and which will be also discussing and expressing in terms of measurable properties whenever we are talking about how to handle various properties kind of thing. So, for an ideal gas throttling process, the what you call Te is equal to Ti, that means basically the Joule-Thomson coefficient is equal to 0. So, if you look at, we have seen this thing how you can apply the first law of thermodynamics for open systems, and in this case there is no reacting flow. This is not a reacting flow, no reactions are going on. In the next lecture, what we will be doing, we will be learning how to handle the reacting flow, right. In this case, the heat exchanger, and then your what you call compressor, and then turbine and other problems what we have seen in case of unsteady, there is no reaction going on, there is no heat release, no chemical reaction going on. So, these are the simpler fluid. We will have to see how we can apply this first law of thermodynamics for the reacting flow in the next lecture. Thank you.